The Hubble Space Telescope and the James Webb Space Telescope observe the universe from space. There are a lot of advantages for observatories being above the Earth's atmosphere, and some disadvantages.
While both telescopes are different, they do have one thing in common. They look across space and back in time. That's right, the light these telescopes is observing is old. It's like looking at a picture taken a really long time ago.
It's like we have our own time machine.
Where we're going, we don't need roads.
This is STEM in 30.
Hi, I'm Marty.
And I'm Beth.
We are coming to you from the Smithsonian's National Air and Space Museum in Washington, D.C.
And we are in front of the Structural Dynamic Test Vehicle for the Hubble Space Telescope.
It was used for a variety of tests and was subjected to the same noise and vibration that the flight telescope would experience during launch, as well as the extreme temperatures of space.
This gives you a sense of the size and scale of the Hubble Space Telescope, which is still in low Earth orbit and still taking pictures.
We are also going to meet some of the people that worked on Hubble and learn about a giant mistake and how they fixed it.
Actually, it was a little mistake with giant consequences.
We're also going to introduce you to the James Webb Space Telescope and some of the amazing people working on it.
Behind me is the Webb Telescope. You can see this is in its basically final configuration, ready to pretty much go into a container to be shipped to the launch vehicle.
I'm Stephanie Milam. I am the Deputy Project Scientist for the James Webb Space Telescope for Planetary Science.
My name is Amy Lowe. I am the Deputy Director for Vehicle Engineering for JWST. This is a bit of a mouthful. My job essentially is to manage the engineering team that's responsible for what you see behind you.
But first, let's explore how these two telescopes look back in time.
When we're looking for the first stars and galaxies across the universe, that is actually looking back in time, not necessarily as like a time machine, we're going backwards in time. It's basically because the light from these objects that's so far away, it takes so long for it to actually reach us that by the time it gets here, it's billions of years old. It's like a photograph that was taken billions of years ago, and that's what we can actually see. So we're looking sort of back in time.
Distance and time are connected when we are talking about looking into space. We often measure distances in space with light years, which is the distance light travels in 1 year. Einstein showed that nothing can travel faster than light.
When you turn on a light in a room, you see the light almost instantly, but even light has a speed limit.
While it took humans around 3 days to travel to the moon during the Apollo missions, in 1 minute, light can travel to the moon and back over 22 times. That's a bit more than 11 million miles.
The light that warms you up when you walk outside left our sun a little over 8 minutes ago. In that time, it has traveled over 91 million miles. But let's go a little farther back.
The distance light can travel in 1 year is 5.88 trillion miles. We use the term light year to represent this distance. We do it this way because the distances start to add up really quickly.
To give you an idea of how far a light year is, imagine that the 91 million miles from Earth to the Sun is only 1 inch. Then the distance light travels in a year would stretch almost a mile.
It's almost unfathomable how far just 1 light year away is, yet the numbers are only going to get astronomically larger from here. To give you scale on just how far these distances are, we're going to talk about how long ago this light had to start its journey to reach us here on Earth. But remember, light years measure distance, not time.
The closest star to our solar system, besides our Sun, is Alpha Centauri, which is about 4.4 light years away, meaning that something traveling the speed of light would take 4 years to travel that distance.
The furthest thing you can see from Earth with the unaided eye is the Andromeda Galaxy. a collection of 1 trillion stars that are about 2.5 million light years away. The light entering your eye set out on its journey 2.5 million years ago. That was way before modern humans, or Homo sapiens, during the Paleolithic period on Earth, and it's the earliest part of the Stone Age.
Next, think about your favorite dinosaur. We know you have one.
Roar, the mighty T-Rex! Let's move back to the time of dinosaurs. More specifically, when dinosaurs went extinct 65 million years ago. We can't see the light from those distant objects without the use of telescopes. In the constellation Ursa Major, or the Big Dipper, there is the spiral galaxy, seen here imaged by the Hubble Space Telescope. The light we are seeing in this image began on its journey when dinosaurs were still roaming the Earth.
The Hubble Space Telescope has allowed astronomers to look back in time to when galaxies were forming. The furthest it has seen is over 10 billion light years to create the Hubble Deep Field Image. It was created by looking in an area that was thought to be mostly empty. It was taken over 10 days and consists of over 342 separate images and has changed the way we view our universe.
The James Webb Space Telescope is an orbiting infrared observatory that will complement and extend the discoveries of the Hubble Space Telescope. The longer wavelengths of infrared light enable Webb to look much closer to the beginning of time and to hunt for the unobserved formation of the first galaxies, as well as to look inside dust clouds where stars and planetary systems are forming today. We're essentially seeing these objects as they were when the light first left them over 13 billion years ago. Scientists anxiously await these images and what they will unveil about the earliest universe.
In order to capture this distant light, telescopes need really big mirrors.
The James Webb Space Telescope is going to be a little bit bigger. Let's compare the sizes.
The size of the Hubble Space Telescope's primary mirror is 2.4 meters, or about 8 feet across.
And now we see the size of the James Webb Space Telescope. It has a primary mirror that is 6.5 meters, or more than 21 feet across. A larger mirror means more light that you can gather, and the more light that can be collected, the further back you can see.
The light that reaches both space and Earth telescopes is very faint, and in the case of the James Webb Space Telescope, even different wavelengths, but it's still light. In a telescope, the more light you can collect, the more you can see.
First, imagine this as an Earth-based telescope, and these represent light. When we drop our light, some of it's collected and some of it isn't, but it's more complex than that. On Earth, we have a little thing called an atmosphere, which is great for us, because without it, we'd be having a pretty bad day. This makes it difficult to observe really distant light. But the more light you can get into the cup, the further distant objects you can see.
This yarn represents our atmosphere. When the pom-poms are dropped, we see that some of the light will make it through, but not all of it. Less light was collected when it had to pass through the atmosphere.
What would happen if we moved our cup above our atmosphere? It would collect more light. That's what the Hubble Space Telescope does. The telescope and a really big mirror are in space above our atmosphere. Let's see how good a job it does at collecting light.
Better than when the telescope was below the atmosphere. Then we have the James Webb Space Telescope. It has a much larger mirror, so it can collect even more light, and it's even further out. Let's see how much light it can collect.
As you can see, being above the atmosphere allows you to catch more light, and the larger mirror allows you to catch even more light. And the light that these telescopes has collected has led to scientific discoveries and some amazing images.
When the Hubble telescope launched in 1990, no one knew it had a mistake.
until they saw the images come back and they were all a little bit blurry.
But NASA had a plan.
They've got people thinking stuff up and people backing them up.
To fix this mistake, it took engineering genius, but it resulted in scientific gold.
Engineering things that have never been done sometimes have issues.
The first images from Hubble were frankly a little disappointing. They were not as sharp and crisp as we had hoped. It turns out that the mirrors had a slightly misshapen form.
This special mirror, 2.4 meters of specially ground glass designed to capture the light of the universe back in time, billions of years, has a problem.
And I'm positive that if we all had written down the 100 most likely problems with the Hubble Space Telescope, not one of them would have listed the mirrors the wrong shape.
We feel that we can characterize the problem, the spherical aberration problem, well enough that we can take advantage of an insurance policy that we haven't talked much about. We started a long time ago to plan a maintenance program. That is, every 3 years we plan to go up with the space shuttle, change out instruments, change out things that broke. In fact, we have in stock, in storage, most of the critical components on Space Telescope.
So we promised that we had a way to fix it, and we put a new camera in with corrective optics in it that would cure the optical problem.
Right as we talk now, we are building a second wide field camera. You can almost think of it, if you've got bad myopia, which you can say our telescope has now, and you put your glasses on, you can correct totally and get 20/20 vision. That's what we would do in the second wide field camera. We would change one little mirror, take out the aberration that the primary mirror causes. That is, if it's a positive aberration, we put in a negative aberration and basically cancel it out. We feel the analysis is only preliminary, but we're pretty optimistic that we can take out all the aberration with the second wide field camera and get us back to the original specification.
We were all disappointed, but all hopeful that something might be done to save this spectacular space observatory. And so the first servicing mission to send astronauts back to Hubble was designed to repair this problem.
To fly what you test and test what you fly would be easier if the telescope were back on Earth. But landing and relaunching could contaminate the telescope or damage it through vibration.
And this big mirror really was the dominant driver. We worked very, very hard to develop, first of all, how distorted was it? How mispolished was it? And then to find a company that could polish corrective lenses that would take care of the problem.
So to make sure the optics will work, the team had to determine the condition of Hubble in space and replicate that on the ground. One independent review panel used Hubble images to determine the precise shape of the flawed primary mirror and the prescription to fix it. Another team had to verify that the corrective optics will work. Teams had to test two optical packages, the replacement wide-field planetary camera and the corrective optics for the other instruments, called COSTAR. Engineers built several independent analyzers to test that they had replicated what the Hubble telescope does to light. No one can predict everything that could happen. The real test will be in space.
5, 4, 3, 2, 1. And we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
Houston, Endeavour has a firm handshake with Mr. Hubble's telescope.
We copy that, Cubby, and there are smiles galore down here.
Broad, let's come on in.
Nobody really believed they could do all of this work, and they did it in fine fashion. Even with some problems along the way. So that brought Hubble back to life, and it kind of took away some of the criticism of NASA because they had now demonstrated that they could do something that had never been done before. We had never serviced a telescope.
Technicians used this to test the procedures and equipment that was used to fix the telescope while in orbit.
There were 5 separate Hubble servicing missions, and many of the tools and procedures they used had to be developed from scratch.
Let's learn more about Hubble from some of these astronauts.
The Hubble Space Telescope is probably the most significant scientific instrument ever created by humans. It's taken over 1.4 million images for tens of thousands of scientists around the world. But the other thing Hubble has done is show us for the very first time really how beautiful and amazing the universe is.
I went to work for NASA and I was hired as a flight controller. So those are the people that work in the control center. And so one of the early missions I did was STS-31, which was where we launched and deployed the Hubble Space Telescope, which was absolutely fantastic. I was on the team that helped develop all those procedures on how they were going to take the arm on the space shuttle and grab the Hubble Space Telescope and move it into position and then let it go into space. And that was just so incredibly special.
The Hubble Space Telescope was launched in 1990. It was designed to be fixed by people in spacesuits, wearing big bulky gloves. But at the time, we hadn't built a space station. We hadn't done a lot of work in space.
The Hubble mission was very complicated and there were lots and lots of things that had to go right. But we had some of the best trainers in the whole world, the best engineering team to design the mission and help us prepare for the mission. Every single thing had to go right, but we also knew that when things went wrong, we had a great team of people on the ground that had our backs that would help us work through it.
The whole entire crew played a critical role in designing our own tools with the help of the engineers that allowed us to be successful on the flight.
I was a mechanism designer at Goddard Space Flight Center designing mechanisms for satellites, and I got involved in the Hubble Space Telescope repair mission. The mechanisms on that mission were power tools and torque limiters and wrenches, and I designed them with my team as if they were spaceflight mechanisms. Really tried to design the best tools that we can that were going to last forever. They're still up there now, going on every spacewalk of Space Station.
We had several tasks that we had to do, scientific instruments that had failed, but we couldn't bring up new cameras to replace them. So we had to learn how to fix them in space. And this involved taking out very tiny screws and pulling out circuit cards. And just learning the new techniques and building new tools to do that was hard on the ground. And then when we were in space, we had to do the same task for real to fix these cameras.
There's the EVAs. I was going out. It was my first spaceflight mission, and it was my first spacewalks. So there was a lot to learn. Probably the most fun I've ever had was just training for the mission. To actually get to go fly it was just icing on the cake.
The repairs we made to the Hubble Space Telescope were a bit daunting. We had only a short period of time to get the work done, and we did 5 spacewalks back to back, day after day, and that was tough work.
So on my last spacewalk, I made a very bad mistake that almost messed up the whole mission really on the telescope, and they came up with a solution. But I remember I was really upset about this, and I had to try to stay in the game and couldn't get too upset because we still had to work through this spacewalk.
But fortunately, we trained for 3.5 years for the mission, so we were ready to go and ready for that task.
And that's the ultimate example of just being part of it, a very tight-knit team. Every big accomplishment is done by a team.
There's always a question after we have visited the telescope whether we were actually successful or not. And so usually when we come back to Earth, it's a few weeks before that first image comes out. And 2 things. One, I'm always really thankful that the cameras work and that we get to see some spectacular celestial object. But also, the whole point of going to the Hubble and putting in new instruments is to improve its capability. So when we put a new instrument in and the pictures come back, they're sharper and have more detail than anything ever seen before. And that's just really fascinating to see.
I think all of us take great pride in knowing that the work that we did is continuing to pay off.
Hubble has changed the way we view the universe.
And the images it has created are absolutely stunning. But how are these images produced?
We want you to learn a little more and try this at home.
Hi, I'm Bryce. Let's do a quick coloring activity. Let's learn more about images from space telescopes. So for this activity, we need a coloring key and coloring page, as well as some crayons. To begin with, pick 6 colors. These can be any color you want. Write them down 1 through 6. This will make our coloring kind of like a Mad Libs, only for coloring. Next, color your coloring page based on the colors you picked. You might be able to make out what it is supposed to be, but make sure you follow your key. Here's my final picture. Can you tell what the stuff is? Usually, we think of an apple being red, but mine is blue. But what does this have to do with images from space telescopes? Let's ask an expert.
Great job! I'm Elise Pagan. I'm a science visuals developer who works at Space Telescope Science Institute, and we are associated with NASA. We take data from Hubble and other observatories, and we make pretty pictures of space.
I'm Joe DePasquale. I am also a science visuals developer at the Space Telescope Science Institute. And like Elisa, my work is to take the data from the Hubble Space Telescope and other telescopes and create imagery and visualizations for press releases or outreach products, and pull all that information together to help get the word out about the amazing science that we do at Space Telescope. My job is to take data from the telescope and turn it into imagery. The way that we do that is we actually go into the archive and pull raw data out of the archive of different objects the telescope has observed. It will observe those objects in multiple wavelengths of light, and that's actually sort of the core of where the colors come from, because we take those multiple wavelengths and we assign colors to them. The longest wavelengths are assigned redder colors, and then as we move into shorter wavelengths, we move to blue. And so when we pull all that together and we've assigned those colors accordingly, we end up with a full color image made up of red, green, and blue.
Kind of a true color representation is what we call it. Sometimes we do with imagery that doesn't have that direct translation. We're dealing with narrow wavelength ranges that are telling us a little bit something more particular or different, kind of like a particular hot gas or dust or composition. And sometimes we have to change that color to get a really interesting image that speaks to the science of what we're looking at.
So the challenge with infrared light is we need to take sort of the same model of coloring that we use for optical and transfer it into infrared. So we expect to get data from the Webb telescope that will have shorter wavelengths of infrared light and longer wavelengths of infrared light. And in general, we'll apply the same principles of giving shorter wavelengths bluer colors and longer wavelengths redder colors to then combine all the data together to make color images.
Alyssa and Joe, how did I do?
The coloring that you did really connects to what we do.
There's very specific colors attributed to certain phenomenon or particular filters, just like in the picture where it's just sky is one color. And then you had like the ground is one color and the sun is one color. You know just by that color that you're seeing that you're looking at the sky. And it's the same thing with things like if you're looking at a galaxy and you know, oh, that magenta, that's where star forming is happening. Or, oh, that's blue in that galaxy. That must be a really hot young star. So it is very similar. And when you color code it in that way, you can learn a lot.
The Hubble Space Telescope is still in space, still doing amazing work. You can even see it pass overhead if you know where to look and you've got dark skies.
But there's a new telescope in town, the James Webb Space Telescope. But it's not a replacement for Hubble. So why Webb?
JWST is a reflective telescope. It works in the infrared. It's designed to detect the first stars and first galaxies that's ever formed in this universe.
So right after the Big Bang, seeing how the first light was actually created.
And so it works in what's known as infrared light.
Infrared light is actually a wavelength of light that's just beyond what we can actually see. So if we could tone our eyes into seeing how hot or how cold somebody was, that would be what infrared light is really tracing, is that thermal radiation.
Our atmosphere actually prevents infrared light from reaching the surface, so a ground-based telescope would not be able to detect these signatures. So we need to launch this into space away from the atmosphere. And to work in the infrared, it needs to be cold. Otherwise, the optics and the instruments are warm, and what it'll measure is instead itself, rather than these light signatures from the very early universe. In order to keep it cold, that's why we have a 5-layer sun shield. It reflects sunlight and prevents it from heating up the instruments and the mirrors.
We want to know how galaxies actually started to form and evolve. Did they start from a couple of stars, or was it a giant energy burst? What actually was that process and how they were formed? We want to know how planets and stars are actually being born in their own dusty areas in space. That's something that we can't see with other wavelengths, so having the longer wavelengths and the infrared really shows us how some of these planets and stars are actually being born. In the solar system, we want to know what the atmosphere of Mars is doing from a more global perspective. While we have rovers and orbiters going around it, they only get that sort of, airplane or local car sort of perspective. When we look at it with a telescope that's a bit further away, we can see the whole global climate of another planetary body. Jupiter and Saturn, the moons around these planets, we want to know what's going on with them.
But the Webb telescope is so powerful that it can do other things. It will track the evolution of galaxies through the entire age of the universe, essentially. And something else that's very exciting, which is if you point JWST at nearby stars, there is a good chance that if these stars harbor planets, that Webb will be able to detect those. And if nature cooperates, and we're very lucky, there are opportunities potentially that we can detect atmospheres
and see if any of them are like Earth. If they have water, if they have a nitrogen atmosphere, carbon monoxide, carbon dioxide, the things that we find in our own atmosphere.
Once you can detect atmospheres, a whole new field of interesting things can open up.
He's looking at me.
Some of our snake friends, including this ball python and most vipers, see in the infrared spectrum. It helps them see their prey. This means that they can see the infrared radiation, which is invisible to the human eye. Let's see how you can learn more about infrared light. The James Webb Space Telescope will be using the infrared spectrum to look at our cosmos in ways we have never seen before.
Any form of matter, no matter how hot or cold, gives off thermal energy. This includes everything like chairs and books and even food.
Everything around us, even the Earth, radiates thermal energy, even stars.
Thermal energy is the primary source of what we call infrared radiation. This is the section of the electromagnetic spectrum just beyond visible light in terms of wavelength size.
We cannot see infrared radiation, but technology allows us to detect and take pictures in this part of the spectrum.
NASA, NOAA, and other agencies use infrared imagery to study the Earth in ways beyond what we can see. The James Webb Space Telescope will collect infrared light and allow us to see back to when stars and galaxies started forming.
Over 200 years ago, Sir William Herschel discovered the existence of infrared by studying sunlight passing through a prism, like you might find in your classroom.
The prism separated all the colors that make up sunlight into an array called a spectrum.
Here's how you can see the phenomenon that William Herschel first observed. He measured the temperatures of the different colors of light and found that the temperatures increased from violet to red.
What he also noticed was what happened just beyond the visible spectrum. The temperature increased even more.
To try this yourself, take a box outside and measure the temperature inside the box in the shade. Then adjust the prism so the spectrum is as wide as possible. Place the thermometers in the blue, yellow, and the area just beyond the red.
You should see the temperatures increase as we approach the infrared area of the spectrum.
It might seem like it's a big jump to go from a prism on a box to the light that the James Webb Space Telescope will collect. But there's more to energy and light than meets the eye. It's like we have our own time machine.
Where we're going, we don't need roads.
This is 7:30.
They're pretty good.
The Hubble Space Telescope and the James Webb Space Telescope are engineering marvels.
Hubble has changed the way we view the universe, and soon Webb will be looking at some of the oldest light, allowing us to see almost back to the Big Bang.
As these images begin to come in, we hope you look at them with awe and wonder, but also a bit of understanding of how they were taken, what they represent, and the science behind the telescopes that took them.
If you like this video, be sure to give it a share and let us know what your favorite part was down in the comments section.
And be sure to follow STEM in 30 on Facebook and Twitter, and subscribe to the National Air and Space Museum's YouTube channel.
We leave you today with some of the stunning images taken by the Hubble Space Telescope.
Thanks for watching.